Yeah, so I thought I would talk about some of the work we're doing in precision agriculture and forestry. Uh, it is an important area, and I'll motivate that a little bit. But first, I want to just say it's been great being in the GRASP lab, and um, my own group has actually flourished over the last few years, and I'm grateful for many people who are pictured on the slide. Besides Colin, I also have, I think, Pratap Tokekar is also here, right? Is he part of the center? Yeah, yeah. So, yeah, so a lot of close ties. We used to have close collaborations through an ARL consortium with folks in aerospace and in electrical engineering. So a lot of close contacts. But since I've come here, and since I last came here, there are 2 new buildings on campus. So clearly Maryland is growing rapidly. Darrell Pines is an old friend of mine, so is the Dean of Engineering. The work I'm going to be presenting is primarily the work of Fernando Cladera, Laura Lipschitz, Zach Ravichandran. Colin, you are old if you need glasses, and I can tell now I can't see those. I have 63-year-old eyes, which are not very favorable. UAU, Wu, Jake Weldy, Igor Spasyevich, and Varun Murli. We draw from a mix of talents, a lot of computer science, electrical and systems engineering, and mechanical engineering. And also work closely with colleagues in the lab. Pratik Chaudhary, young assistant professor, Kostas, who's been in the field for a long time, Nick Martini, also young assistant professor who's joined us over the last, actually 5 years ago, George Pappas, Alejandro Ribeiro, CJ Taylor, no longer young, but great collaborators. So I want to talk a little bit about the field of aerial robotics. First, it's a big field, but you'll notice that most of this is really taken up by the military and consumer robotics. And these are things that, yes, you could be interested in, but I think the real applications going forward are in agriculture, mining, health tech, areas where really aerial robotics can have a positive impact on society. And so in my lab, we work on autonomy. We work on autonomy in small, excuse me for that, for tightly packaged systems, so size, weight, and payload constraints, something I've been doing for the last 15 years. The video on the left side shows a swarm of 250-gram robots with all computation sensing on board. And so we try to do that at larger scales as well. As you go into more unstructured environments with obstacles, you need more sensors, obviously, and more processing. And we not only look at how robots can control in a coordinated fashion, but also communicate. The question of what information needs to be communicated depends on what individual robots sense. And that's something that's hard to model, and we've increasingly found that learning-based approaches really work well. So graph convolution network, for those of you who don't know, is essentially the generalization of CNNs, but to arbitrary graphs. We've found that by training small teams on lots of data, you can actually extend to large teams with some assumptions on the size of the graph, some continuity assumptions. And so that's worked very well for us. I'm not going to be talking about that, but instead, I want to talk a little bit about applications to precision agriculture. I know this is one of the things that there are folks here that are working on it, but this is a fairly big industry, and it's also an industry that's greatly stressed. First, because of climate change, the yield per square foot in the United States, and actually globally, has been declining. Pathogens, pests, et cetera, add to the complication. So it is a fairly large value proposition if you can somehow restore that efficiency. So we have an NSF ERC centered at Penn with collaborators at Purdue and Florida that essentially looks not just at autonomy, which I work on, but also the sensing fabric, the communication fabric that's needed to deploy these systems in the wild. The last thing I'll add is that globally, agriculture accounts for about 70% of the water consumption. And this is, again, a big deal. Freshwater consumption, I should say. This is, again, a big deal. So if you can make things more efficient, you also save in other ways as you think about the food and water ecosystem. So our grand vision is to have this feedback loop where you have essentially sensors, robots gathering data autonomously, and then models for controlling the system in this case being the entire agricultural system. And so how do you draw a feedback loop around that? And of course, the time constant for this is quite large. You want to do it over a growing season. Collecting data is hard. It's not like you can go on the internet like the natural language folks do and scrape data from a web. Here you have to collect the data yourself, much of it. And so we're making, it's a starting point in that direction. A closely linked field is precision forestry. And again, if you live in the United States, 33% of the world's, of the US surface is covered by forests. And provides about 20% of the freshwater ecosystem. So lots of things to be done here, but again, the forestry experts will tell you that they don't fully understand the impact of various things that happen around us, anthropogenic factors that drive the disruption to forests, not just forest fires, not just climate change, but also pests and so on. So if you can measure forest growth, and what makes the forest actually degrade, that would be an incredible contribution, not just to the economy, but also to the environment. The last thing I'll just say is that during COVID, actually before heading into 23, 24, there was a lot of interest in looking at carbon credits as a way to control the growth of emissions. So if you want to control greenhouse gases, the best way to do it right now is to grow forests or to maintain forests. Unfortunately, the political climate is such that the support for that has waned. People projected in 2022, 23, voluntary carbon markets would be like $1 trillion economy. All that has fizzled out. But the long-term issues still remain. If you want to do carbon sequestration, forests play an important role. And cultivating forests is important. The last thing I'll say about forestry, I went, when the rebuilding was being built, I actually came and visited as we built our own AI and data science building. And one of the things I'm motivated to do from my research is to consider a mass timber construction. So normally you think of efficient buildings and everybody thinks about energy consumption in the building. And they go after platinum certification, LEED certification, that is. But in fact, just like if you look at your phones, there's a lot of energy that's spent in actually making the phones. Actually building a steel and concrete structure is just a lot more expensive than a mass timber construction. So this is built from North American wood in central Quebec. And it reduces the embodied carbon by about 55 to 70%, depending on how you evaluate that. So I would not have become aware of these issues if I had not gotten interested in forestry and precision agriculture. And one of the, in my unbiased opinion, a beautiful building on campus, the most beautiful building on campus is now mass timber. So that's by way of introduction, but I want to now switch gears and tell you a little bit about aerial robotics. In 2010, when we started working in this field, we didn't have the right sensors, we didn't have the right compute. We did have platforms, but a lot of the sensing was enabled by motion capture systems. And so yes, we figured out how to do nonlinear control, planning, et cetera, at very high speeds. But the state estimation, the biggest challenge when you go outdoors was through motion capture systems. And so the trajectories were pre-planned in the sense, well, there's a little bit of dynamic replanning that could happen, but mostly based on knowing what the environment looks like. When you go out on the field, of course, you cannot do that. And so over the last 15 years, I would say we've now gone to platforms like these, which are not small platforms. They're much larger. The design for longer flight time, they use lithium-ion batteries instead of lithium polymer batteries, flight time about 35 minutes. And all the computation is done on board, including deep learning techniques where the inference has to be done on board because you might not have access to more powerful computers, certainly not access to the internet. And you have to figure out what sensor stack to use. So that not just includes sensors for state estimation, but also mapping the environment and determining what's the best trajectories to pursue. So the platform we have weighs about 4.5 kilos, 4.5 pounds, and has essentially a combination of Intel CPUs, also NVIDIA GPUs, but everything designed so that you can carry things on board. And it's important when you think about the calculation that you're burning roughly 200 watts per kilo of payload that you carry. So to have something that's lightweight is important. And unlike what's happening today with all these large language models, where compute is essentially considered cheap and people don't penalize compute, although some recent efforts to build smaller models do consider that. But for the most part, we don't think about that. But here we pay for every operation, if you will, that you do on board. More importantly, we also pay for every bit of information you extract from the environment. So it's an interesting systems challenge as you think about the problem of gathering data and functioning autonomously. That drives the electrical system and then finally drives the mechanical system. It's very different from conventional ways. When you build cars, you build a mechanical system, then the electrical system, and then you slap on compute on board. And here it's the other way around. The autonomy sort of drives the mechanical system design. So very quickly, we have a sensor stack that we use, which is fairly modular. Again, uses the LiDAR, the best sensor for varying illuminations. And then you also use conventional cameras, also thermal cameras, and of course an IMU. So this sensor stack is now fairly robust. There's a ROS compute on board. We're transitioning to ROS2, and we can hand this off to farmers, and they can collect data for us. Or fairly naive people who know how to teleoperate drones can slap this on board, and it can do everything for them except the navigation. So some of the use cases we have, so here you can see on the right side of the tractor, it's mounted on the tractor. It can be on hand-carried carts that they use for gathering fruit, for example. Or in forestry, you have scouts that walk around and measure trees. And while they're doing that, there's a sensor on the backpack that essentially measures the properties of the tree. So this is our sensor stack. Increasingly, though, event cameras are proving to be very promising. And so we're also looking at how we might have downward-facing event cameras, which offer much better images, particularly low illumination conditions. And then forward-facing cameras for navigation, again, in dynamic environments. But more importantly, again, in environments where there's a lot of there's a variation in the illumination as opposed to just objects going past you. So I think this is a game changer for robust autonomy. We're yet to be at a point where we can actually use this reliably, but we're certainly going in that direction. Let me tell you a little bit about the sensor stack and the architecture we use. So as I mentioned before, we rely on the IMU, cameras, LiDARs as inputs. And the key thing is to extract semantic information, objects of interest. So if you're obviously in an agricultural environment or forest environment, you want to extract trees, fruit, other kinds of objects. We use that not just to gather information of interest, but also for mapping and for localization. So our state estimation algorithm, for example, relies on our ability to reliably extract semantics and then localize based on that. So we use off-the-shelf tools. The one that is shown here is from GT-SAM, a package developed by Frank Dellett and colleagues at Georgia Tech. So that semantic SLAM algorithm is sort of the backbone for state estimation as well as for mapping. And then we use a bunch of things to plan locally and globally. Globally, if you want to map a forest, for example, there needs to be a coverage algorithm that figures out how to do this. Likewise, if you're trying to count fruit in an orchard, another application, you need a global planner. But the local planner is the one that figures out where to go to get most information locally and how to avoid obstacles. And then that, of course, drives things that are fairly well commoditized now: position controller, attitude controller, state estimator, et cetera, et cetera. Moving ahead, I want to just show you what the semantic map does. So if you look at that central block here, you will see this happening in real time. You see the robot essentially poses, which are shown in the middle, and the semantic map that's constructed. Again, in forests, trees are very reliable, and so you want to make sure you locate the trees so that you can localize, but also so that you can actually get that information. So in most forestry applications, researchers and practitioners are interested in the number of trees, where the tree diameter is, and how much carbon is contained, which is something we can get naturally. So if you do this optimization or robot poses and object models, you will beat any standard state estimation algorithm, for example, visual odometry and so on. So the first algorithms we developed were called SLOAM. SLOAM had to do with LiDAR odometry and mapping. But over time, we now have a combination of LiDARs and cameras that contribute to this. So this is mostly work of Shu Liu, who's a postdoc at Stanford now, and Stephen Chen, who started a company. I'll tell you a little bit about this company. He's no longer with us, but we still collaborate with him. If you look at planning, on the left side, you see the basic approach to planning, which is you're essentially planning locally inside that box, while you have longer-term trajectories that are being planned based on the mission specifications. Those are the green trajectories. You could see the camera images, one of the camera images at least, inset. So that is used for visual odometry sometimes, and other times it's used for identifying the type of tree, the type of crop that you're interested in. The planning is all driven. This is Jake Weldy's work, but essentially we now have not just aerial platforms, but also under-actuated manipulators on these platforms. And so there's a little bit of differential geometry and mechanics where we map the dynamics of the system into a flat Euclidean space, almost Euclidean space, if you ignore the S1 singularity. But that differential flatness allows us to plan in this sufficiently smooth flat space, which is kind of the backbone of many of our planners. I won't spend too much time on this. This is fairly old work. I'm happy to share more details if somebody's interested. The key, though, here is that we're trying to plan sufficiently smooth trajectories. So in all our planners, we're trying to minimize derivatives of the position R and derivatives of the yaw angle psi. And if you can find a sufficiently smooth trajectory that satisfies the constraints on the position, that is the obstacles, for example, or on the visibility, which actually comes from the yaw, then you're guaranteed, because these are flat coordinates, you're guaranteed you'll satisfy the system dynamics. So this is pretty important. It frees you from the problem of figuring out what the mechanics are and allows you to focus on constraints that are mission constraints. One thing I wanted to point out, and this will come back, I'll come back to this later, you're always minimizing this functional or a fixed time interval. Usually T is unspecified. So in most papers that you see, somebody makes up the T and said, this is what we're going to do. So increasingly, if you want to go fast, obviously you want T to be as small as possible, but if you do that, you'll violate constraints and you might not find trajectories. So finding this unspecified time horizon is important. And again, I'll talk a little bit about this as we go forward. So here's the entire system at work, and I'm going to skip the first few minutes of this, but I'll just give you, it's not playing. So this is what the robot sees as it navigates. This is what it maps. And there's the robot and some students running after it, trying to keep track of it. The two cameras, what they see. Um, this is sort of the local map that again is used for trajectory planning and for state estimation. This information is used mostly for gathering mission level information to satisfy mission level objectives. Um, we do a lot of our testing in New Jersey in the Wharton State Forest. And that's one of the problems is, as the federal government puts restrictions on where you can fly, where you cannot fly. So finding forests where you can fly is a bit is challenging. Fortunately, we have partners at Virginia Tech in the forestry department, and so we use their forests to do many of our flights. So in this particular, I just want to mention in this particular hardware, the hardware configuration, of course, we have the VIO module. So we get poses at 30 hertz from the camera, but we also get poses at the same rate from the LiDAR. So there's an interesting fusion problem there. We use a combination of an Intel processor and a Jetson GPU to run all of these systems on board. So this is a model-based architecture, so a very conventional way of looking at things. And of course, today everybody will say, well, why do you have to model anything? Why do you need equations? Why can't you just throw it into a learning-based approach? And there's some merit. So pretty much everything I've talked about, you can think about learning from data directly. The inputs are the same, the outputs are the same, but you can try to learn the state as a function of time, on real time. You can build a scene graph as opposed to just mapping the obstacles and trying to figure out how to navigate between the obstacles. You can figure out how to navigate the graph. You could build a symbolic planner. It doesn't have to be the kind of planner I just showed you with a cost functional. And then you can learn the map in the process. And of course, at the end of the day, you can also learn control. So this is a viable approach. It's something that's worth thinking about, but, as opposed to just dismissing it. And it's conceivable that this kind of an approach would be more efficient to design and to deploy. Potentially more flexible. You go from one environment to another environment, maybe it generalizes. But I'll just point out the obvious, that this is a data-intensive way of doing things. So when you don't have the data, when you don't have the prior experiments, not a great way to get started. Not to say a model-based approach couldn't be used to gather data, which could then lead to a data-driven approach to deployment. And at the end of the day, you want something, if you deploy it, and if you want to give it to folks to use it on your behalf, you want something that's safe, something that's explainable, something that's trustworthy. These are all big question marks. But maybe in the future, we'll get into these kinds of systems. We'll see more of these kinds of systems. The first self-driving cars were developed in 1980, when I was a grad student, actually, 1987, by Ernst Dickmans in Germany. Although if there are any CMU grads here, you'll probably say that NavLab came before that. I don't think so, but anyway, but it's 1987. And you think about, sorry? 80, oh, you're 81, okay. I'm sure John has the history here. But my point is that if you think about the 80s, we're 40 years out now, and we still don't have cars that are safe, explainable, and trustworthy. Although a lot of great vehicles being developed in China with lots of interesting capability, and not to say folks like Waymo who are doing things here. So I want to talk a little bit about some of the research issues that we're pursuing. So trajectory planning for fast flight, even though I showed you these early videos, and our early work in 2010 to 2015 showed fast flight, this is still challenging. I want to talk a little bit about that. I want to tell you how we use multiple robots in the forestry setting. And then the rage of the day, how do you use foundation models in robotic missions? So maybe touch on that. How much time do I have? Oh, plenty of time. Okay. So let me go into the nuts and bolts of how we might think about fast flight. So first of all, it's an optimal control problem. You have a cost functional, I alluded to that, but you also have time that you're trying to minimize. And so in this flat space, you can basically write it down as a linear set of linear differential equations. The constraints on the environment and the constraints on the input might make it more complicated, might make it non-convex, but ultimately at the end of the day, you're solving this optimal control problem. So there are two approaches to solving this. So one is you use an optimization-based approach. The second is use a search-based approach. So we've tried both. So Sikong Lu, who's now at a Chinese self-driving car startup company, and uses this for self-driving cars, use sort of this motion primitives approach where you very quickly develop a search tree and then you're able to explore this in real time. And it works amazingly well in cars as well. If you use either approach, the fact that you have a high-dimensional dynamic system relative to degree 4, the fact that you're operating in a non-convex environment, the fact that you have to explore across different homology classes as you look for trajectories, all this makes challenging. And then, of course, you have a partially known environment. So you really can't travel very fast if you don't know what's ahead of you. All of this constrains how quickly you can operate. But basically, there are two coupled optimization problems. And now what we see increasingly are off-the-shelf planners that consist of two pieces. One is a front-end planner that kind of thinks about what the path is. And so this could be just a geometric path without thinking about all the constraints, what makes it ugly. And then a back-end planner that does all the smoothness optimization with dynamic constraints. So that's the part I just alluded to. That's an optimization problem. But by decoupling these two into two optimization problems, you're essentially acknowledging that you're not going to solve the second problem optimally. You're going to rely on something that's known up front. That's basically a skeleton of a trajectory, and then you can try to optimize it using an optimal controller. The first one allows you to sift through multiple homotopy classes and pick the one that makes most sense, either from a coverage standpoint or from a fast navigation standpoint. So this video is fairly old, but it illustrates the basic idea that you're trying to decompose the environment into safe corridors, and then you're trying to model each flight corridor, safe flight corridor, by a combination of overlapping convex sets. In this case, these are ellipsoids. We also use polytopes for the most part. And then you try to optimize the trajectory that constrain it to lie inside these polytopes. These are some initial outdoor experiments. These are fairly old. But if I want to describe the math to you, on the left side you have this optimization formulation. So here you're dividing the trajectory up into m segments. Each segment is constrained to lie inside a polytope, and you try to match up boundary conditions at the overlap areas. You make sure that the corridor constraints are satisfied. In other words, the trajectory does not stray outside the corridor. And then you enforce continuity at the intermediate waypoint. So this is a very classical approach to doing trajectory synthesis. But what makes it hard is it's a high-dimensional problem, the constraints on the left side, and you got to make sure that you satisfy all these constraints. I don't have to emphasize that you're trying to solve for, essentially, so if you use a polynomial basis for this, you're trying to solve for the coefficient c, and then you're also trying to solve for the time. So the time intervals for each segment is not known up front. How long you spend in each polytope. And surprisingly, that turns out to be the bottleneck. So if I knew up front, if I had an oracle that told me this is how much time you spend in segment 1, segment 2, segment 3, et cetera, then the problem is actually trivial. So it all boils down to finding the optimal time allocation across the segments. So the main challenge is, if I know the time segment t, the allocation of time t, then the time optimal trajectory optimization problem is essentially an optimization problem for specified time intervals, and that is a convex problem. So this is easy to solve. Again, the challenge is if the time intervals are not known, okay? So this is where, for the first time, we've started using learning and inference in the loop to try to solve a problem that we cannot solve in real time using conventional methods. So this network is called AlloCnet. It's actually a fairly simple network. More importantly, it's how we think about this. So if you think about a robot navigating a complex environment, the inputs are the point cloud. You're just getting all these obstacles. You know where you are. You know where the end state is. And from the point cloud, you can infer corridor constraints quite easily. And so again, remember, I already have an initial path that informs the formation of the corridors. So what we want to do is to learn a function that maps initial and desired conditions to a sequence of safe corridors, and more importantly, a sequence of optimal waypoints. So this is work by Yue and Igor. And so we learned this time allocation on the fly. So again, you're looking for polynomial coefficients, but in this quadratic program, you're assuming you know what T star, the optimal time allocation is. And the coefficient matrices here, A, G, et cetera, are now functions of that time allocation. So 8 years ago, there was an interesting paper on using differentiable optimization as a layer in neural networks. So we use this idea. That particular paper has nothing to do with dynamics or robotics, but Yue saw this paper and thought it would be a good way to think about these differentiable optimization for learning time allocation. So again, going back to the quadratic program, Q, A, and G are parameters of the QP, and these essentially can be encoded as weights in the neural network. Because there's optimality here, you know what the necessary conditions are, and it turns out that these necessary conditions form an implicit function that are smooth. The function is smooth unless there are some exceptions where it's not smooth. For the most part, it's smooth. So under generic assumptions, it's actually smooth. And then you use the conditions and their gradient to backpropagate gradients of the primal solution towards the optimal time allocation T. So that's the basic idea. So your loss function then is a combination of how much time you take, and you can try to minimize that. And the second term and the loss term is something that comes from large language models. Folks in the NLP community know this. This is sort of the stopping length. It's a technicality, and I don't want to spend time on that. But basically, you're trying to minimize the amount of time. At the same time, you're satisfying the necessary conditions for optimality inside the QP that you see on the right side. So again, we want to run this in real time, and this inference actually happens in 1 millisecond. The training time, I'll get into that in a little bit. But here's the idea. On the left side, you see the point cloud in which you're operating. The maximum speed is about 2 meters per second. The maximum acceleration is about 3 meters per second squared. Not very high, but remember, the robot has a finite field of view. So given that finite field of view, it's really hard to fly more than 2 meters per second because the stopping distance, if you assume a braking of roughly 1G or even 2Gs, you can't really develop to that speed in a cluttered environment. Anyway, but that's what you're seeing in this video. So just some idea of how these results would work. 1,000 randomly generated three-dimensional maps. For each map, 100 randomly generated initial and final conditions. We have about 100,000 parameters in our network. And this you can train fairly quickly without thinking too much about it. And we're now convinced we can get it down to a few hours. But you basically get to 87% success rate without learning. We're at 50%. So this makes a big difference. I don't have to tell you this. If you're trying to fly a robot with limited battery in a hazardous environment, if you can go much faster with the 87% success rate, you cover missions with a greater degree of efficiency, and of course, safety is a big deal. So this is one line of work, and what we're now trying to do is to do the same thing with autonomous flight, but with event cameras. This is work by Anish Bhattacharya with my colleague Nick Martney. Again, forest flight, where we're trying to go directly from what we see in the event cameras to trajectories with a view of maximizing coverage. Some initial results, I won't talk too much about this today. So how do we take this for multiple robots? So again, remember, if you're in a forest-like environment, the main challenge in navigation is not the robots themselves, but the environment with obstacles. So with multiple robots, again, in agriculture, what happens is you don't have a network, you're not always connected, so the communications is opportunistic. So for the most part, the robots do their own thing, but when they talk to each other, they reconcile their information with what their partners have, and then try to optimize based on that. So I mentioned GT-SAM, which uses this language of factor graphs, the idea that you have poses, you have landmarks, which in our case are semantic landmarks, and you have links that connect your pose to the observations you made with these landmarks. So each robot has its own factor graph, but when they come into proximity and they actually detect each other through the communication network, they basically ask if they know where they are relative to each other. If they do, then they can take the factor graph from the neighboring robot. So ideally, you want the raw measurements. If everybody has the same raw measurements, this is actually from a system theoretic standpoint, that's the rigorous solution. But we can never guarantee that. We never have communication, the bandwidth to essentially get all that information. So essentially what these robots do is keep their own raw measurements, but they also have the factor graph from neighboring robots. And they plan based on the assumption that the other robot's factor graph is accurate, so they don't have to cover areas that the other robot has covered. If they don't know where the other robot coordinate system is, then they basically have to go through a search process. This is an embarrassingly trivial way of doing it, expensive way perhaps, but basically you have a sliding window that examines all possible poses until they find something that matches. There's variations of this from John Howe's group at MIT that actually makes it more efficient that we're also using, but it's a very simple idea really. So again, these two, you can take as many factor graphs as you want in this approach and then plan motions that are optimal for the robot, being aware of what the other robots have done. So this is the key, this is the sort of the key way of thinking about multi-robot problems. So here are two robots traveling along two independent trajectories. Actually, rather than play this video, I'll just show you what they find. So this is sped up by a factor of 4 to 5. And here you see three different robots doing the same thing. But because they know each other's relative coordinate system, either opportunistically or by deliberate planning, you can essentially combine these maps. And what we're looking for, again, is an efficiency that allows you to speed up operations by n, where n is the number of robots. Again, this is important in large forests. If you go to a orange orchard in California, easily 20,000 acres, you'll be all day if you had a single robot with a battery charger. So we really want to deploy many of these from a truck. So the same approaches are also used in urban environments. This is our lab. You see a couple of different aerial robots. And we develop maps like the ones you see in the bottom left. Here, the semantic objects of interest are poles, light poles, cars, trees, buildings. If you do this, in addition to getting better state information, you can also exchange information more efficiently and work on a network, which is basically the equivalent of a 802.11 network, outdoor network. Lastly, I want to say a little bit about how we're thinking about the use of foundation models, particularly large language models, but also vision, open vocabulary models. And of course, not a day goes by where you see a startup doing manipulation, raising $1 million, $1 billion these days. I remain skeptical of everything that's happening in that space, and I would love to talk to any of you who feel otherwise, because I'm still trying to learn this. But the area I've seen these models to have immediate impact is really running these missions in environments you've never been in before, and missions that are not well specified. So if you spend time getting a robot to become autonomous in a given environment, you'll find most of your time is spent in actually setting up the problem and the dreary work of actually programming. So the setup to automation is 90% of the challenge. The automation is not. I want to just show you an example of something which is poorly specified, but this is Zach and Varun's work. So this is our lab. It's a prior map collected by UAV. And here's the mission. If you say the mission is to move supplies from the lab, which by the way is the white building on the left side, to the supply truck parked across the road to the north, if I tell you this mission, you immediately understand what it is. If I have to translate this to a robot, it requires a lot of work. The map, explaining what north is, what's a parking lot, what is not, and so on. And in this particular experiment, the map has been disrupted. There's construction in the middle, which means what I knew before is no longer the case. Again, humans have no problem. So you have a couple of problems here: partially known map, incompletely specified mission, and you want the robot to understand your mission. So it's a problem of specifying the mission, translating that into tasks, and then doing motion planning from task to task. The low-level stuff that I've just talked about, I'm going to assume is solved. But the planner has to infer which is the parking lot you want to go to, what area needs to be explored in order to extend the map to confirm the fact that this unknown area is actually navigable or not. You have to confirm the path is clear, and then you have to navigate to the parking lot. So a lot of uncertainty. And again, you understand exactly what those highlighted words means, but to explain to the robot is quite tricky. So this particular work just uses LLMs for reasoning and planning. And so the planner that we have is called SPINE. There's a SPINE stands for semantic planning. It's not my favorite acronym, but incomplete natural language specifications. And so you do some upfront validation because the robot has certain motion primitives. It knows what's possible, what's safe, what's not. It is not, for those of you who do formal methods and model checking, no, we'd like to get there, but that's a big lift. And it interfaces with this low level of control and perception, which we understand fairly well. So again, on the left side, you have some system setup, a partial map, user specifications, but then the possibility for the robot to interact with the human on a regular basis. So recently we conducted this experiment, and it is quite recent. I don't even have the video embedded in this. But let's say you have a team of aerial and ground robots, and you say, there's a chemical spill, we need help in collecting information. It's not too hard for example, for ChatGPT to come back and say, well, I need to look for barrels in this area that might contain fuel, for instance. And that's inferred. And then might also come back and say, I want to look for people. And so you can tell the UAV in this case, can you look for barrels and people? And the ground robots interacts with the UAV. I'll show you a video that illustrates this particular scenario. It's a 1-minute video, and it plays through. Whoa, that doesn't work. Just give me a second. I'm sorry. Is this? I didn't know how to do this, but I'm trying to slide my QuickTime window into this. Maybe I can just. Oh, you did? Oh, it's in the bottom. Nice. There we go. Thank you, sir. So I wanted to just go back to the beginning. So this is, again, our campus. The problem setup I just told you about. The difference is there are 2 ground robots and 1 aerial robot all doing this at the same time. And the main way the robots communicate, or the representation, is really through an aerial graph, which basically tells the ground robots where the roads are, where the trees are, where the buildings are, and so on. Again, the nodes connect opportunistically to the human. As and when they get this information, you can see the aerial robot doing the semantic mapping, and then communicating that when it sees the ground robots, or when it can talk to the ground robots, the semantic map, and they both guide each other. We start with a satellite image for reference, so we have a partial map, but of course we don't know the details of the map as we go through the process. And you could see the exchange of information between the aerial robot and the ground robot. Right now, all the language models run on a server, but we have a recent call submission that shows how we can distill our models into a 5 gigabyte model with about 7 billion parameters that runs on an aerial robot. Again, I remember I told you about all the constraints we have on payload on the aerial robot. So in the main screen, you see the aerial graph that's being built and the ground robot finally picks up the barrels. And again, the assumption here is that the only things of interest are barrels and people in a chemical spill. But this is where I think vision language models can come in. If you really know what the mission is, you can specify the mission, and you know what objects to look for. And of course, enough perception experts in the audience, we know how to connect concepts in language using clip features, for example, to actual objects that you can detect in the environment. So pretty excited about that. I want to wrap up by just hitting one more theme. Obviously, we're very interested in taking this technology for deployment in the wild. We have startups that are working on some of these ideas, but I want to come back to agriculture. So TreeScope is an open source database that we have released, and I liken it to Kitty, which of course bootstrapped a lot of the self-driving car efforts. And there's a similar one for aerial robots as well. So TreeScope actually does this for trees. So if you go online, look for TreeScope, you will see LiDAR data set acquired from robotics platforms. There are ROS interfaces to that. There's also images taken from our cameras that are superimposed on that. And so to our knowledge, this is sort of the first robotic data set which is exclusively collected in agriculture environments. So it's not just trees in forests, but also these are pistachio farms in California. So we get ground truth data. So in the forestry business, they measure what's called DBH, diameter at breast height. So we have DBH measurements that are acquired by human beings, as well as DBH estimates that you get from robots. Robots are obviously more accurate, and more importantly, they can cover lots of trees in the same amount of time. There's a paper that describes all the details, which was published in ICRA last year. So let me, and I'll also say the one thing that the experts who work on forestry want is physical sampling. So it's really hard just from images like this to detect the type of tree. So what the experts do is actually look for leaves that have fallen on the ground. So we've been thinking about how we might collect those in a more systematic fashion, guided by aerial robot measurements. The company I told you, this is the Stephen Chen and Elizabeth Hunter that started this company. It's really, as it says, intersection of nature and infrastructure. So they manage assets which are in forests. So different types of companies are interested in this. Obviously, those that do timber harvesting, timber management companies, but also utility companies that are interested in mapping out forests or trees. Anytime there's a storm, power outages, the most common cause for that is trees falling on power lines. A more mature company is Exxon, and they do GPS-denied navigation, really complex environments. They call it level 4 autonomy. So the idea is that you let the robot loose, and it goes out, it maps everything without putting humans in danger. So this particular company excels in operating in mines, underground mines, areas where fortunately the FAA has no jurisdiction, and construction sites, which are, again, privately controlled. The central product, which is really this something like our sensor pack, actually works on any robotic platform. So you'll see it on backpacks. They have it on the Boston Dynamics Spot. They can operate in forests, ravines. So lots of cool stuff. Just a comment. I talked a little bit about AI. I want to just say it still remains, in my opinion, fairly overhyped. Of course, computer vision, natural language processing, synthesis, et cetera, has completely changed how we go about approaching this. But I still don't see the impact in manufacturing and robotics. In the management supply chain, the logistics, yes, but not at the low level. There's a little video. The first robot was installed on the shop floor roughly when I was born, 63 years ago. We still don't have the dexterity of this 2-year-old who's absentmindedly assembling these Lego blocks. I also have pictures of videos of my grandson who's 18 months old, and the robots can't do what he does. This is it's something that I think is a challenge for us. It's a very powerful technology. Everybody talks about physical AI, embodied AI. It's still not there. The last thing I'll just say is I'll take a dig at some of my people that are not my favorite. This was an article that came in the Wall Street Journal. It's an old article by Christopher Mims. We still have an accountability crisis. Of course, with Elon Musk, it's more problematic than just this accountability crisis, but just promising things that we know don't work. And it's something we have to be careful about. I think the other thing I also worry about is this sort of mixture of, so most of us, at least I got into robotics because of science fiction, right? So that inspires you to do things that you don't imagine. You say, can you build machines that can do that? And I have a suspicion that most DARPA program managers also do the same thing. Wow, let's build this, right? They have this far out vision, and it's exciting as engineers. But science fiction becomes reality, and that reality plays out on the battlefield. So it's something I've started worrying about as dean, is how do we inspire kids to work on the right problems? And the folks on the right are not great inspiration, right? And so we have to look inwards as faculty, as PhD students, as postdocs, to train our undergraduate students. So it's something, I don't want to spend too much time on this. The last thing I'll just say is, if you go to Sydney and you look at the Sydney Harbor Bridge, there's one pin that holds this bridge together, just one pin. And I can just imagine the engineers sweating over that pin. How big does it need to be? What are the stresses? What's the factor of safety? We just don't do that in robotics. And I think anytime you have a machine that moves, and particularly now we have excavating machines, bulldozers that are all autonomous, there's no consideration of all of this. So it's something worth thinking about, but I just want to thank you for inviting me. And most importantly, thank you for distracting me from the chaos on campus. Appreciate it. As two AI experts, yes. No. I'd love the, yeah.
Fastness and so on and so forth. Okay. Because this, I think, is missing.
Yeah. So I completely agree with the first part of what you said, which is anytime we use learning, it is in the context of models. So I think philosophically, maybe because of the time we got trained, we have similar views on this. But no, I think that's important. The question is, how well can you estimate uncertainty from the outputs of deep neural networks? And that too, we look at seriously, but unfortunately, the evidence for that is empirical. So today, you look at most papers, they do ablation studies to figure out what's important, what's not important. What they don't do is figure out how important is it, the last decimal point, for example, these lightweight models, distilled models, how much of that is necessary. And that yields some information in robustness, about robustness. So yesterday I was at a talk by Bill Daly from NVIDIA, the chief scientist, and he was basically describing, at the end of the day, it is how you represent information through numbers and how many operations do you have to do on the GPU that essentially drives power consumption. And those things also tell you something about the robustness of the calculation. That's just philosophically, at least, how I'm thinking about this, but I'd love to get more ideas on
But the
this.
interaction between the model-based and data-driven actually can help you a lot in reducing the number of samples you need to estimate the uncertainty.
Correct.
As long as you're willing to do the trade-offs between performance and the uncertainty.
Correct. So I think model-based approaches can allow you to gather data, which then can drive the learning, and then you can do apples to apples comparison, which is sort of how we do this.
Okay.
But my colleague at Penn, Dinesh Jayaraman, and his student, Jason Ma, who's in the job market, I mean, they do things that I don't know how to do in a model-based approach. So for example, I don't know if you guys have seen this gone viral. They've got this legged robot on a yoga ball balancing itself, or doing dexterous manipulation with fingertips. It's something, 20, 30 years ago, I tried. Ken Salisbury, very smart guy, he tried. But just using data, they're able to accomplish this. So combination of using models to train it, and the robots get better and better and better over time based only on data. It's a limited setting, so you can't send it out in the wild. But if I know if my life depends on balancing myself on a yoga ball with 4 feet, that problem you can solve using model-based approaches and AI. So,
Okay. Thank you.
Dinesh. No, I do not disagree. It is a model-based approach. In this case, the model was the human. And over time, you collect the data. And then you figure out how to do pure data-driven approaches. And that's the way people are doing it. But let me just say that a lot of the self-driving car solutions that are based on LiDARs are just not viable from an economic standpoint. If you go to China, there are startups that are doing camera-only solutions. My former student, Xiaoji Shen, who do a lot of the UAV work, and he said, this is too small a market. He's now doing self-driving cars. He sells units that are about this kind of a baseline, stereo cameras. He also uses depth sensors. And the unit mounts behind the rear view mirror in a car, and he's selling 100,000 of this a year to all the EV companies in China, right? How is that working? They're not doing level 4 autonomy like Waymo is, but they're doing level 2 autonomy. And I tell you, I've driven in this, and I've just been so impressed by how they do this, right? So again, they are leveraging this. The advantages in China, there are a lot more drivers than there are in the US. And I'll tell you, his company has 1,000 people working on one thing. Again, something we don't have. So I'm not saying it's not possible, but in many cases, you don't have the data. In forests, you don't. Construction sites, you don't. So how many construction sites do you have to map before you go to the N+1 site and you actually know what to do? That was my point. Yeah. Likewise, that child manipulating blocks, I guarantee you this, you don't have to see those blocks to know how to put things together, right? So there's a fundamental, going back to the system, we don't know how to do that. Totally. Yes. But that's not what we're doing in self-driving cars. That's not what we're doing in self-driving cars. Well, that's why no, I understand that, but I'll tell you, I have trouble attracting students to my labs. They say, why do you do this? Why not just use the learning? I showed you that block diagram. They say, why don't you just learn the whole thing? And I humor them. I let them try things out. It's without that knowledge, it's hard. So I agree with you. Okay.
So Vijay, your point is well taken as data, but even like you look at Google Gemini Robotics, right? Google has gotten billions of hours of video. So now they're saying, just like you showed your grandson, there are billions of parents all over the world putting YouTube video. So I totally agree with you what you're saying, and even John is saying, let's see how far we can push the data. If partially working, let's use it. It's not perfect.
Look, I'm here. I'm having fun. I want some controversy. So, but I think it's a great debate to have. So I'm not totally dissing this, but I'm just saying this is we're not as far along as we think we are.
I agree with that.
Yes. So I was just wondering what the cost of the sensor package you have on those UAVs is.
So sorry,
Yeah.
I can't tell.
Oh, yeah.
Introduction. Thank you.
Tell that.
Yeah, so the driving, I mentioned this about Waymo. So we use the least expensive, reliable LiDAR you can get, which is the Ouster LiDAR. So that drives up the cost. So you're looking at a $10,000 package.
Yeah.
So if it wasn't for the National Science Foundation, we would not be able to supply these to farmers and collect the data.
And they're not attritable. And I mean, if you said you had an 87% success rate at 2 meters, I'm just thinking about
No, that's for autonomous navigation.
Mhm.
But for data collection, it's much, much better, of course.
Mhm.
In fact, it works in smoky conditions and dusty conditions. It can detect, tiny wires. So it's actually quite reliable.
Yeah, no, I'm from New England, and one of the first thing I thought of with the forestry and agriculture, I mean, is maple syrup. You should go to some people. There are some people who are doing incredibly good, tech farming stuff with maple syrup, and I think it's something you might want to look into.
Yeah, no, absolutely. I think I'm very bullish on this field.
Mhm.
Again, commercially, it's a bit of a challenge because the value added by robotics, I mean, it's hard to evaluate.
Yeah, no, the value add is leak detection during peak season. That's the value add. If you can do that autonomously.
I know, but try to monetize it and try to make the argument for a $20,000 robot. It's hard.
That is hard.
All right, I'm going to have the last word on this so that we can all go to break. I am on Vijay's side, but I'm also on the data side. I want to say that the very fact is the reason the model doesn't work all the time. Model works most of the time. In fact, how many of you have actually gotten onto an aircraft that was driven by the data? No. If you're on that aircraft, you will be scared to death, right? All aircraft, all the jets are still driven by a still controller. Yeah, tradition.
Everyone, airport base, experiment the turbulence. I can say the thing. Don't make that. Have to do everything that
I agree. No,
that's what she's
John,
saying.
that's what I say. I want to say the very fact is.
But you said the model cannot do anything. Can you
Yeah.
know the work, right? L1 controller for feedback of choreographed maneuver.
I don't think that's what she said.
No, I am saying that the very fact is the traditional model still works. And in fact, it works most of the time. Where it doesn't work all the time is when we have very complex interaction, physical interaction, which the model has approximated. This is kind of like talking about linear controller versus higher order controller, right? And why do we approximate on those situations? Because they are complex. The interaction is mutual and it's complex and it's exponentially hard. This is where some of the data capturing helps. But by the same token, where we see the promise of where the data interaction, the data is actually capturing that interaction, it's going to be the kiss of death if we continue on this data path. And the reason is the potential pairwise interaction is exponentially high for all the infinitely many dynamic interaction we can possibly have in the real world. Simple thing, frictional contact. Different frictional coefficient will arise from different material interacting with each other. There is no way in the world can you possibly ever capture all these pairwise interaction. So I think the way to go is to marry the data-driven approach with the model-based approach. Take the model that we have as the initial and refine with the data that we have and change and adapt to each one of the scenario. So I'm the proponent of differentiable programming, differentiable physics, differentiable geometry, because I believe that's the way to go.
So you came back where I came back, okay, in the first stuff. And the way we do it is as follows, okay?
Yeah, I think you're in violent
You
agreement.
always have to have that last word.
But I mean, the point is, but I want to give you details, all right? So you take the model-based approach, you find out where you're going to run into trouble, right, from the model-based approach, and that can be for various reasons. Missing approximations in modeling, environmental, and it is exactly there with you cleverly, carefully experiments or simulations to figure out how you can improve.
Yeah,
That
I mean, I
gives
think
you-
this time allocation problem is one where,
Right, that gives you a
I mean,
lot
you
of
know what you
advantage.
can do with models and you take it to the next level. So I'm not denying that, yeah.
No, I don't want to get the final word, okay? I'm just telling you things we have been working about, that's the right word, for 5 years. Now, finally, somebody.
But by the way, the last slide I wasn't going to show, but I saw John in the audience and I said, I'm going to put that in there. No, it's great.